Hello and very welcome to the presentation of Transition of the African Power System to Renewable Energies, a case study. My name is Robert Gaugl and I'm from the Institute of Electricity, Economics and Energy Innovation of Graz University of Technology in Austria. A short introduction of why we're doing that. We know that climate change is happening and is already here. And even in Africa, we can see that wildfires are increasing, there's floods that are increasing, and longer time of droughts that are increasing. And we see that the humans do have an effect on the global surface temperature. And Africa already sees some severe effects on the water supply, food security, and human health. And so Africa's power system also needs to shift to renewable energies for that. In the next two slides, I want to introduce you and give a quick overview on the current state of Africa's power system. The African power system is divided into 5 so-called power pools, as we can see in the figure on the right side. There's the North African power pool, or sometimes also called COMELEC. And then we have the Eastern African power pool, the Southern African power pool, the Central African power pool, and the Western African power pool. Some countries belong to more than one power pool, and those are the ones that you can see here are a little bit striped. Depending on the source, it's a little bit different which country belongs to which power pool. So we did our best to reflect the current status in this figure. The goals of these power pools are to increase trading between the member states. So if there's like a power plant outage in one country, so that the other countries can help out in such a situation. And so this should lead to higher system reliability through better interconnections of the members in the power pool. And this should also lead to cheaper electricity prices due to the economies of scale. Though the level of development differs greatly, so the North African power pool and the South African power pool are the ones that are more developed, and the least developed one is the Central African power pool. And as we can see here in figure 2, 4 out of 5 power pools depend heavily on fossil fuels. The only exception is the Central African power pool, where hydro has a larger share, but also electricity demand is very low in the Central African power pool because it's the least developed power pool. And currently it's using lots of power from the rivers of Congo, for example. But if we look on Africa as a whole, we can see that about 80% of the electricity is produced by fossil fuel power plants, and then hydro, wind and PV, nuclear, and biomass follow. So, and it is expected that the electricity demand will increase significantly in the next few years and decades. And if this power system is not transitioned to renewable energies, then it will contribute a lot of CO2 and therefore contribute a lot to the climate change. And that's the motivation of why we wanted to build a digital twin of the African power system. And for that, we used the LEGO model, which is an open source model co-developed at our institute, and it stands for Low Carbon Expansion Generation and Optimization Model. It is very flexible and modular. As you can see in the figure 3 on the right side, there are different model options that can be turned on or off as needed. For example, you can run it as a MIP with unit commitment decisions, or as an RMIP. You can run it with a single node network or with the grid network in mind, with either a DC OPF or a simplified AC OPF. Or you could also choose options for demand side management and so on. There are also some political constraints that can be turned on or off as needed, like you could set a minimum green production, you could set a maximum carbon budget, or you could investigate firm capacity. The model itself is usable for operation optimization or for power plant and or grid investment planning, so TEP or TAP. The temporal framework of the model is very flexible, so you could either run it in a chronological way, like say our 1 to 8760 for 1 year, or you can run it with representative periods like representative days, which we will do in this case. The input and output data is in the Excel format, and the code itself is completely written in GAMS. For the methodology, you need time-independent data and time-dependent data to model an electricity system. The time-independent data is the grid data and the power plants, and the time-independent data are the hourly demand per node, the hourly capacity factors per node or per power plant for PV and wind, and inflows for the hydropower plants. And because we do not run the model here in a chronological way, we feed the time-dependent data into a clustering algorithm to get one representative day in this case. Problem is, where do we get this data from? Because it's not that easy to get data for the African continent as it is in Europe or as it is maybe in the US. So for the time-independent data, the grid data is taken from the OpenStreetMap project. For those who don't know OpenStreetMap, it's like a combination of Google Maps and Wikipedia, where everyone can contribute data to this map. And to our surprise, it has very good grid data for the African continent. And so we can see here, those are the lines, electricity lines that it has for 110 kV and up. And we use this data, but you can't use it directly in our model because it's too detailed, and a tool, we call it grid tool, to transform this OpenStreetMap data into data that can be used in electricity models. So it identifies nodes on a holistic basis and then simplifies the lines so that they're going from the start node to the end node. So we have the grid data is checked, and power plants. We also looked into open source databases, but they're either not available for the African continent or they are lacking too much capacity. Therefore, a commercial database is used, which has its own problems because it doesn't have any GPS information of the power plant, and it doesn't say, okay, which is the feed-in node. So we wrote another script that transforms the city in which the power plant is located to GPS data via a geocoder. And then with a geographic information system program, we choose the closest geodesic node and set this node as the feed-in node. So that is our assumption in this case. For the time-dependent data, we took the yearly electricity demand from the African electricity energy database and made synthetic hourly demand profiles for every country and every node out of it. And the hourly capacity factors for wind and PV per node are downloaded from Renewable Ninjas. So we have like a demand per node for 8,760 hours, capacity factors for 1 to 8,760 hours, and so on. And we took this data and feed it into a clustering algorithm with a K-Medoids algorithm, and used it to transform the hourly data into just one representative days in the first case that we use in this case study. The simulation itself is run as a short-term unit commitment problem for the year 2019 to verify the results of the model with actual data, and is then run as a generation expansion model for the 100% renewable energy case study. The model is run as a mixed integer problem with a DC OPF, and the GAPS version 39.1.1 is used on a standard PC with an Intel Core i7 11th gen and 32 gigabytes of RAM. And it took about 173 minutes to solve the model for the whole African continent. So for the verification, we used the year 2019 and compared the simulated results with actual data from the African Energy Database, which can be seen here on the right-hand side. The North African Power Pool, South African Power Pool, Eastern African Power Pool, and Western African Power Pool. And we can see that the simulated results are always lower than the one from the actual data. And there's a reason for that, because we just use one representative day where the clustering algorithm chooses one actual day that represents all 365 days of the year. And it chooses that based on, of course, not only the demand, but we also fed in the capacity factors for wind and PV. And so there's not one day that perfectly represents all of the days. And so in this case, if we just take the demand of this day and multiply it by 365, the demand is exactly is lower compared to the African Energy Database, and it's exactly lower of the amount that is the case here. So I will come back to that later, but for our first result, we know what is the problem here, and we will fix it in a future update when we run a model with more than one representative day. But for now, let's use this one representative day. So in our case study to transform the African power system, we added so-called candidate power plants that the model can invest into on every node. And we used unlimited candidate power plants so that it can add as many PV or wind power plants as it wants to reach a 100% renewable energy case study. And the result is to cover the African continent with 100% renewable energy, at least the countries that we included in our simulation, which I should add are just the countries where we got grid data from OpenStreetMap. So all the countries, that's also the reason why the Central African Power Pool is not included here anymore, because this power pool is so underdeveloped that it doesn't have sufficient grid data in OpenStreetMap, and therefore we can't simulate for it. So to cover the continents that we simulated with 100% renewable energy, an additional capacity of 180 gigawatt of wind and 32 gigawatt of PV is needed, which would result in electricity production of 432 terawatt hours of wind, 107 terawatt hours of hydro, 97 terawatt hours of solar, and 0.4 terawatt hours of biomass. I should also add that we said nuclear is not renewable in this case, and therefore that's the reason why it's not here anymore. So as a conclusion, we have to, in order to transform Africa from adjustable thermal power plants to renewables, we need a planning tool. And therefore, we developed a digital twin of the African power system. And in our first case study, we see, okay, to transition only to renewable energies, we need about 222 gigawatts of wind and solar capacity added, which is around $16.5 billion of investment costs. But we also know, okay, we have to improve our model. So what's the outlook? The first thing that we are currently already doing is to add more representative days. So with that, we better depict the variances in demand and renewable energy production. So we can have, like, if we run it with 7 representative day, we have like a demand that better represents the spring, a better day that better represents summer, winter, and so on. And then the next step is that we plan to limit the candidate investment power plants based on the available potential per node. So in the first case study, we said, okay, we have unlimited candidate power plants, but we want to base them on the actual potential that is available per node. And in the last step, we also want to add storages, because currently, of course, the model invests or chooses to invest more in wind power plants, because wind is also available during night hours, where solar is only available during the day hours. And if you can't store the energy that is produced during day hours, then PV is not that attractive to the model. So thank you very much. If you have any questions, please let me know.